Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 2 on properties of parallelograms. Now, we started talking about parallelograms in the last lesson, right? And they're a type of trapezoid with one important difference, and we'll be reviewing that in just a moment. It's important to distinguish as we go through the unit on quadrilaterals the difference between the definition of a figure, i.e. what makes a figure that type of figure, like a trapezoid. A trapezoid is any quadrilateral that has at least one pair of parallel sides, versus the properties that end up coming from that definition. So today, what we're going to be doing is we're going to be looking at the definition of a parallelogram, and then we're going to prove the properties that then arise from that definition. So, without further ado, let's get into the definition of a parallelogram. All right. Parallelogram, any quadrilateral with two pairs of parallel sides. Again, we've got side AB, side CD, they're parallel. Side BC, side AD, also parallel. And that's it. That's the whole definition of a parallelogram, okay? The definition of a parallelogram isn't, it's a four-sided figure with opposite sides parallel and they're the same length and opposite angles are the same and this and that and whatever. No. What makes a parallelogram is the fact that it's got two pairs of opposite sides that are parallel. And that's it. But what's really amazing about that is how many additional properties are sort of born from that one. So let's start getting into those. All right. So in exercise number 1, what we would like to do is first sort of take a look at the major properties of a parallelogram and then go on to prove them. So let's see what exercise 1 asks us to do. In the diagram below, parallelogram ABCD is shown with AB parallel to CD, DC, and AD parallel to BC. Diagonal BD is drawn with certain angles numbered. Letter A asks us to use tracing paper and a ruler, carefully copy the parallelogram, and verify that opposite sides are of equal length and opposite angles are of equal measure. All right. So let's talk about these two first, and then we'll kind of verify them using tracing paper, and then we'll go on and prove them. Now, again, these are properties that come from the fact that the opposite sides are parallel. They are not part of the definition of a parallelogram. So what I'd like you to do is take tracing paper like what I've done. I kind of traced out my parallelogram in red, and then verify that the opposite sides are the same length, and that the opposite angles, like angle A and angle C, I'm not talking about angles 1, 2, 3, and 4. They're not actually angles of a parallelogram. They're angles created because I put this diagonal in. But we just want to verify that the opposite angles are also equal. So take a moment and do that. All right, let's go through it. One thing that's kind of cool about the tracing paper I have is I can do all of it sort of at the same time, but let's take a look. So here I've got my parallelogram all traced out. If I want to verify that AB and CD are the same, I can actually just sort of translate this down right like that. So same length there. If I want to verify that BC and AD have the same length, I can kind of just shift it over like that. And probably my favorite thing to do, which is to verify that opposite angles are equal, what I'm going to do is I'm going to take this whole parallelogram and I'm going to rotate it 180 degrees. All right, so watch what happens when I do that. Angle C rotates up to angle D, and although it's not quite on top there, there it is, right? Likewise, I mean, we can also see that angle B went down on top of angle D, so those are also congruent. Those are two of the major properties of parallelograms. The opposite sides, both pairs of opposite sides have the same length, and both pairs of opposite angles also have the same length. So now, let's take a look in letter B at how to prove that. Let me read through the problem for you. We would now like to prove these two properties of parallelograms using Euclidean proof. Okay, so that proof we were doing a lot of back in Unit 3. It is enough to show that AB is congruent to DC, and angle A is congruent to angle C. We're going to fill in the reasons to the proof. Now again, we could easily prove that AB is congruent to CD, BC is congruent to AD, angle B is congruent to angle D, all of that. But as soon as we sort of prove that this is congruent to that, the logic or the reasoning would be the same as proving that this is congruent to that, likewise with the angles. So let's take a look. All right. Now, this is where that diagonal comes in, and I want to kind of, before we get into the steps of the proof or the reasoning of the proof, I want to just kind of make a comment about this. All right, we did a lot of work back in Unit 3 on proving that triangles were congruent, and then maybe using those congruent triangles to prove that parts of the triangle were congruent using CP-CTC reasoning, okay? And what we're going to be doing consistently throughout this unit when we try to prove things about quadrilaterals is we'll be dividing them up into two triangles and then trying to prove something about those triangles, which will then go on to prove something about the quadrilaterals. So even though normally a parallelogram wouldn't necessarily have this diagonal drawn, we draw it in. Now think about this again. Right from the get-go, all we really know about this figure is that AB is parallel to CD and that BC is parallel to AD. That's basically it. So let's take a look. We're going to now prove, right, at the end of the day, we're going to prove that AB is congruent to DC and angle A is congruent to angle C. So what I'd like you to do is taking a look at the picture, okay, see if you can fill in the reasons for this proof. All right? Pause the video and take a few minutes on this. All right, well, let's walk through it. Well, the first statement I have is that ABCD is a parallelogram, and that's obviously just given to me, right? That's what I'm starting with, okay? Now, the second line says that AB, let me mark this up, is parallel to DC, and that BC is parallel to AD, all right? Well, why is that? Well, you can say it in two different ways. You could say, look, both pairs of opposite sides are parallel in a parallelogram. Or, and I think this is completely okay, you could just say it's the definition of a parallelogram. All right? Pay attention to what your teacher says in terms of what he or she would prefer in that step. Okay, but now we get into a little bit more complicated business. I now have the statement that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. Now, what reason do we put down there? Well, it gets a little wordy, and it goes something like this. Alternate interior angles are congruent when parallel lines are cut by a transversal, right? You remember that? The angles of the Z, they are going to be amazingly important in this unit, all right? If I know that that is parallel to that, and then I draw that diagonal in, then that angle, angle 1, and I guess angle 2 are congruent. And likewise, if those two sides are parallel, then my Z kind of looks like this, and that angle is congruent to that one. 3 is congruent to 4. All right. Now, just as a side note, you definitely don't want to put something in number 3 like definition of alternate interior angles. Because the definition of alternate interior angles is, hey, look, I got a couple lines, I cross them with another line, this angle and this angle are alternate interior. In other words, they're on either side of the transversal, and they're on the inside of the two lines. It has really nothing to do with parallelism, all right? But when the two lines are parallel, alternate interior angles are congruent. And you could get away with that. When two lines are parallel, alternate interior angles are congruent. Again, I would suggest not just saying, alternate interior angles are congruent, because they aren't always congruent unless the two lines are parallel. All right, let me get rid of that. Just a little, it's been a little while since we've done geometry proof. Okay, now I'm going to say, whoops, that BD is congruent to itself. That's pretty easy. That's the reflexive property. Always, always, always. Whenever I say that a side or an angle is congruent to itself or equal to itself, it's reflexive. We're looking in a mirror, looking at our reflection. Finally, think about this now, right? We're now able to say that triangle ABD is congruent to triangle CBD because we have an angle equal to an angle equal to an angle, and a side equal to a side, and that side's between the two angles, so that's the angle-side-angle theorem. But now think about this for a second, right? I now know that this triangle is identical to this triangle. And because this triangle is identical or congruent to this triangle, I can now say AB is congruent to BC, Well, we can also say that AD is congruent to BC. I can do that, that'd be fine. And I can also say that angle A is congruent to angle C, and that's because corresponding parts of congruent triangles are congruent. All right? Now again, I want to pause for a moment because this proof sort of sets the tone for how all other Euclidean proof is going to work in this unit. We've got a quadrilateral, we know something about it. We want to prove something else about it. So we draw in one or possibly both of the diagonals. That breaks the quadrilateral into two or possibly more triangles. And then we use triangle proof and the 5 triangle congruence theorems, side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg, to then prove that 2 triangles are congruent, and then we use CP/CTC reasoning to prove that either 2 sides or 2 angles of the quadrilateral are congruent. It's kind of neat, all right? And we now know, based just on parallelism, that opposite sides of a parallelogram are the same length, and opposite angles of a parallelogram are the same measure. Let's take a look at letter C really quickly before we go on to the next exercise. One of the things that kids get confused about, especially with parallelograms, is those diagonals that are drawn in. And in fact, many students will assume that the 2 diagonals of a parallelogram are always the same length. So letter C says, draw in diagonal AC using a straight edge. Are the 2 diagonals congruent? Test using tracing paper or a ruler. If not, which one's larger? Or maybe longer, either way. So go ahead and play around with this for a second. All right, let's go through it. Again, one of the things that's nice for me is I'm able to just sort of take this parallelogram, okay? I know that this one is diagonal BD, and if I just simply take it and I start to rotate it, what I can see now, not easy to rotate when you're not looking at it, there we go, is that most certainly this diagonal, which was BD to begin with, is much longer than diagonal AC. So they are most certainly not the same length. And we can say that BD is longer. Right? At least in this case, BD is longer. All right, so generally speaking, parallelograms do not have to have diagonals that are the same length. We'll eventually see some special types of parallelograms where the diagonals are the same length, but in general, they're not. There's a shorter one and a longer one. All right, let me just kind of move this one back up to here really quick, give you a moment in case you need to fill out any of those reasons, and then we'll move on to the next problem. All right, let's go through it. Exercise number 2. Now, we're going to go back to the coordinate grid. And again, before we move on, let me just sort of like set the stage for future lessons in this unit and other ones. We now have the tools of coordinate geometry, and we also have the tools of Euclidean geometry to work with. So we can explore quadrilaterals both by using things like the triangle congruence theorems and CP/CTC, like we did in the last problem, and also using coordinate geometry tools like midpoint, slope, and distance to also verify things. So let's jump into exercise number 2. On the diagram, quadrilateral RSTU is shown with vertices R03, S96, T61, and U-3, -2. Letter A, prove that RSTU is a parallelogram using coordinate geometry. All right, so we're now going to do a proof, okay, that this is a parallelogram. But again, that goes back to what the definition of a parallelogram is. It is a 4-sided figure with 2 pairs of parallel sides. Now for coordinate geometry, parallelism is all about slope. Okay, so what I'd like you to do now is calculate the slope of all 4 line segments, lay it out in a nice neat way, and then we'll come back to the proof. Take a few minutes to do that. All right, let's go through it. Real systematic. let's start with RS, okay? Its slope is going to be 6 minus 3 divided by 9 minus 0, which gives us 3 divided by 9, and of course that reduces nicely to 1/3. Now I'm going to do ST. Please notice I'm not saying that RS equals or ST equals. I'm saying, you know, RS colon, and then I've got an M with the slope. To actually say that RS equals 1/3 sort of implies that the length of RS is 1/3, not its slope. So be careful about that. So ST, the slope, 1 minus 6 divided by 6 minus 9 equals -5 divided by -3. And anytime you have a negative divided by a negative, make sure to turn that positive. All right, 5/3. Let me now do the slope of TU. All right, that just did not look like 2 dots. There we go. The slope of TU is going to be -2 minus 1 divided by -3 minus 6, which is going to be -3 divided by -9. A negative divided by a negative is a positive, and then we get it to reduce to 1/3. And finally, the slope of UR, M equals, let's see, 3 minus -2, all divided by 0 minus -3. In the numerator, that's a 5. In the denominator, that's a 3, and there's nothing I can do about that. Now take a look at this. I've got RS with a slope of 1/3, and I've got TU with a slope of 1/3. I've got ST with a slope of 5/3, and UR with a slope of 5/3. So I can now say that RS is parallel to TU, and I can say that ST is parallel to UR. Now those are kind of like statements. My reason is because, I can't get a B/C here to save my life. Let's try one more time. Because slopes are equal, all right, and I have one last little piece, which is kind of that concluding statement. Now I'm going to say RSTU is a parallelogram. Hello, grid, because it has 2 pairs of parallel sides. Now, eventually, we'll see other ways to prove that a figure is a parallelogram in the coordinate plane. But this is the one I stick with the vast majority of times, right? Because it follows the definition of what a parallelogram is. It's a 4-sided figure with 2 pairs of parallel sides. We know that parallelism occurs when 2 slopes are equal, so why not calculate all 4 slopes? These 2 slopes are equal, so parallel sides. These 2 slopes are equal, so parallel sides. Therefore, RSTU is a parallelogram because it has 2 pairs of parallel sides. All right? Now, take a look at B, right? It says show that RU is congruent to ST using coordinate geometry. So one of the things that we proved in the last exercise is that opposite sides of a parallelogram should be congruent, which means that they have equal length. Let's verify that right now. Prove it for this parallelogram in the coordinate plane by using the distance formula. Let's go through the first one together, right? So for RU, all right, we want to find the distance between points R and U. All right, so what do we have? It's a little bit tricky because they're a little bit far apart, but we've got -3 minus 0 squared plus -2 minus 3 squared. All right, -3 minus 0 is obviously just -3. All right, -2 minus 3 is -5. All right, when I square 3, I get 9, 25, and I get the square root of 34. Now, a little note before we go on and have you work through ST, which hopefully will have the same length. All right, square root of 34 can't actually be simplified. Its only factors are 2 and 17, neither of which are a perfect square. But even if you could do some simplifying, since 34 isn't a perfect square, right? If it's the square root of 25, make it 5. If it's the square root of 100, make it 10. If it's the square root of 16, make it 4, right? But if it's the square root of a non-perfect square, there's absolutely no need to simplify it. There really isn't, because ultimately what you'd like to do is work through what the length of ST is, and if it's also root 34, great, wonderful. Anyway, take a moment now and actually work through what the length of ST is. Hopefully it'll also be root 34, and then we'll take a look at it. Okay, let's go through the problem. So, ST now. All right, what's its length? Well, here we go again. ST, we've got 6 minus 9 squared plus 1 minus 6 squared. Not quite looking like a 2. There we go. All right, here 6 minus 9 is negative 3 squared. 1 minus 6 is negative 5 squared, and I think you can probably see that we have it. All right, and that's literally all we need to do. There's really nothing else there, because what it means for RU to be congruent to ST is that their lengths are the same, and there they are. They're both the square root of 34. Again, there's no need to simplify it. There's no need to take the calculator out and figure that that's, you know, whatever, 5.8 something. I don't know. Not so good with the square roots just in my head like that. Leave it as the square root of 34 in both cases. All we wanted to do was show that they were the same. Now, there's one more thing that we want to do here. All right, and I'd like to use the midpoint formula to figure out what the midpoints of the two diagonals are. Okay, so in letter C it says, using the midpoint formula, find the midpoint of diagonals RT and SU. What observation can you make about these? What does this tell you about the diagonals? Draw them in to visualize. All right, well, we've kind of lost the coordinate points, so we definitely kind of want to take those down. Maybe I'll put them right here. R0, 3, S9, 6, T6, 1, and U, negative 3, negative 2. All right, so this thing is asking me to find the midpoints of diagonal RT and the midpoint of diagonal SU. So let's do a little bit of review. Let me find the midpoint of RT and then have you do it for SU. So for RT, right, the midpoint, remember, is the average of the x-coordinates. The x-coordinates, 0 and 6, divided by 2, and the average of the y-coordinates, 3 plus 1, divided by 2. All right, that's going to give me 6 divided by 2 and 4 divided by 2, and that looks like the midpoint of RT is 3, 2. All right, again, R and T, not R and S. I'm looking for the midpoint of the diagonal, right? So if I connect R to T, right, and S to U. So why don't you go ahead and do the same thing, find the midpoint of SU, and then we'll go through it, all right? But take a minute, it shouldn't take long. All right, let's take a look. Easy enough. SU, let's see, we've got 9 plus negative 3 divided by 2, and 6 plus negative 2 divided by 2. That's going to give me 6 divided by 2 and 4 divided by 2, and that's going to give me a midpoint of 3, 2. Wow, I'll be darned, right? They have the same midpoint. Okay, so I guess that's our observation. And then we'll talk about what conclusion we can make. But first, let's draw them in really quick, okay? I actually want to draw in those midpoints. I'm going to go grab a ruler really fast, and we'll draw them in then. So let's take a look. Let's get our diagonals drawn in and then plot that common midpoint and talk about what it means, if we can. All right, so while I'm doing this, you should be taking your own ruler and drawing the diagonal in. All right, there's our diagonal, SU. And now let's get our diagonal RT drawn in. And of course, then we had our midpoint at 3, 2 right there. All right, so RT, SU, and that common midpoint at 3, 2. So what does that really tell us when two line segments intersect at a common midpoint? Any thoughts? Well, what it means is that the two diagonals, at least of this parallelogram, bisect each other. All right, they cut each other in half. So let me extend this a bit. The conclusion is the diagonals bisect each other. And what's fascinating is they always do. It's another property of parallelograms that's quite important, the fact that the diagonals of a parallelogram will always bisect each other, which means they have the same midpoint. Now, we haven't proven that yet, but we will in the next exercise. So let's go ahead and take a look at it. All right. Given parallelogram MNPQ, shown below, or right to the right, with diagonals MP and NQ intersecting at point R, prove that MP and NQ must bisect each other. All right, so again, right, let's really kind of think about this for a moment. Essentially, I'd like to prove what we observed in the last part of the last problem, i.e., if I've got a parallelogram, okay, then I prove based on simply what a parallelogram is and what I've now proven about a parallelogram. Keep that in mind, right? Our old phrase in geometry, once you've proved it, you can use it, even in a proof, okay? Now I've got more things about a parallelogram. I know the opposite sides are parallel. I know opposite angles are congruent. I know opposite sides are congruent, right? I have quite a bit more about parallelograms I can now use in a proof. But all of that put together, I want to now prove that somehow the diagonals bisect each other. Now, let's think of this kind of a little bit backwards. What would I need to be able to show in order to show that the diagonals bisect each other? Well, somehow, I have to show that this line segment's equal to this one, that NR and RP are the same length, and that NR and QR are the same length. So keep that in mind. I need to show that that and that are equal lengths. A little bit harder for me. That and that are equal lengths. That sounds a lot like needing to get two triangles congruent in order to show that the corresponding parts of the triangles are congruent. And if somehow I was able to prove that the triangle up here, NRN, was congruent to the triangle down here, PRQ, well, then that would show me that this was congruent to that, CPCTC, and this was congruent to that, CPCTC. So I'm outlining the proof in my head. But do I have enough to know that this triangle and this triangle are congruent? Well, what do I know based on the fact that it's a parallelogram? I know that MN is congruent to QP because we now have proven that opposite sides of a parallelogram are the same length. What else do I know? Well, I know the opposite sides are parallel. But that would tell me that angle 1 is congruent to angle 2, right? Because those are alternate interior angles. Likewise, though, angle 3 would have to be congruent to angle 4 because those are also alternate interior angles. I hope you see that. And now I have enough, right? I have an angle congruent to an angle, a side congruent to a side, an angle congruent to an angle. I can now prove that this triangle is congruent to that one by ASA. And once I know they're congruent, I can say the corresponding parts are congruent, and that'll get me that bisecting. See if you can put it all together in a formal proof, and then we'll go through it. All right, let's do it. Now, one of the tricky things about proof is that even in a proof that's not all that difficult, like this one, there's probably quite a few different ways that you can do it, orders that you can do it in, but let's start off with the basics. We're starting off with a parallelogram. That's just given, okay? That's what we're starting with. It's a parallelogram. That's basically all we're given. All right. Now, what we were immediately able to say was that MN and QP were congruent. Opposite sides of a parallelogram are congruent. Please don't say the definition of a parallelogram. The definition of a parallelogram has nothing in it about the opposite sides being congruent, only the opposite sides being parallel. So that would definitely be incorrect to say definition of a parallelogram. Right? On the other hand, I can say that MN is parallel to QP, and they're saying the definition of a parallelogram is perfect because the definition of a parallelogram is that opposite sides are parallel. So that's good. Okay? What do I get from that parallelism? I get that angle 1 was congruent to angle 2 and angle 3 was congruent to angle 4. Because alternate interior angles are congruent when parallel lines are cut by a transversal. All right. Again, probably the least amount you could write there is alternate interior angles created by parallel lines are congruent. Don't say definition of alternate interior angles. Don't say definition of parallel lines. None of those are correct. But I now can say that triangle MNR is congruent to triangle PRN, okay? And that is simple, the angle-side-angle theorem. Let me get this up here. I can now say that MR is congruent to PR, and that NR is congruent to QR, all right? And that's due to CP/CTC, right? Corresponding parts of congruent triangles are congruent. And then NP and QN bisect each other. Why? Uh-oh, that just went out of nowhere. Why? Well, that's the definition of a segment bisector. Right? And again, there it's okay to say definition because literally the definition of a segment bisector is a segment which cuts another segment into two congruent segments. It is what it is. There's a lot of segments in that. But that's kind of a neat proof, isn't it? Let me pause for a minute and allow you some time to write anything down you might need to. Now again, one last comment before we move on from this. I noted that there's lots of different ways that you could do this. For instance, you could have said, you know, line 1, MNPQ is a parallelogram. You could have gone with the sort of the parallel sides and the equal angles, then gotten in the equal sides. That would have been fine. One key thing that you can't do is you can't use CP/CTC until you've proven that the two triangles are congruent. It's one of the biggest flaws in logic that students have, and it will wreck an entire proof. You know, if you have to use CP/CTC reasoning, but you never prove that two triangles are congruent, you can't use it. You just can't. You know, it's like using vertical angles are congruent, and then there's no vertical angles. So just watch out. All right, let's move on. Where'd that thing go? Here we go. All right, I guess that's it. That's the whole lesson, right? Now, the purpose of today's lesson is really to show how we could take a definition of a quadrilateral, specifically a parallelogram, and prove other properties that come from its definition. So simply by knowing that the opposite sides of a parallelogram are parallel, we were then able to prove three extremely important properties of parallelograms. 1, that their opposite sides are of equal length. 2, that their opposite angles are congruent. And 3, that their diagonals bisect each other, which is equivalent to saying that their diagonals have a common midpoint. Okay? So we're going to then continue this kind of exploration in the future lessons by looking at additional special types of quadrilaterals. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.